Okay, let us start. So welcome everyone to this webinar of the Best of Water Systems Research series by the Center for Water Informatics and Technology at LUMS. In this series, we aim to showcase distinguished research in water systems, and there is not a short enough list that we could have made of the best of water research and not have included our speaker today. And I'm very honored, we all are very honored to have Dr. Siva Palan in our midst. He claims to be only a hydrologist, but he is also practically a sociologist, also even some say a philosopher. And he has truly helped shape the field of hydrology in its earnest. So I'm very honored to be able to introduce him. He holds a BS in civil engineering, a master's in water resources engineering, and his PhD in the same field from Princeton. He spent 17 years in Australia, the University of Western Australia, as a professor of environmental engineering. He is an acclaimed researcher and has published many articles spanning over a wide range of topics, including effects of heterogeneity and scale, flood frequency, eco-hydrology, and water balance and water quality modeling. He has also, in his doctorate work, he also introduced the concept of the representative elementary watershed, and he has been the executive editor of the Hydrology and Earth System Sciences Journal and was founding chair of the International Association of Hydrological Sciences Decade on Predictions in the Ungauged Basins Initiative. He is also the co-founder of the new subfield of socio-hydrology. He will be talking on the same topic shortly. He has also received several awards for his research contributions, which include the John Dalton and Alfred Wegener medals of the European Geosciences Union and the Robert Horton Medal of the American Geophysical Union. He was joint recipient of the Prince Sultan bin Abdulaziz International Prize for Water, awarded in recognition of his role in developing and leading the new field of socio-hydrology. So before I hand over to Dr. Siva, I will invite Dr. Bakr Mohammed, the director of the Center for Water Informatics and Technology, to say a few words.
Thank you, Talha, and assalamu alaikum to everyone, and good morning and good evening to our colleagues and friends from around the world. Like Talha said, I mean, it's really a distinct honor for us to be hosting Professor Siva Palan. Of course, we will be giving maximal time to hearing the professor himself, but I just wanted to make a connection, a very quick connection with what we have been doing at the center in the last few years, and how Professor Siva Palan's work has really inspired us to do some of the work on the Indus Basin. Just to quickly mention, a few years ago when we started our journey into looking at the Indus Basin, really this whole idea of human-water interactions, of how social networks, they interact with resources, I mean, that was something that was puzzling us. We did not have the appropriate background. And we were first led into literature that we found out was called socio-ecological systems. Of course, people like Eleanor Ostrom, they were really the towering figures there, and we kind of got inspired from her work, and still get inspired from her work. And that was where Talha's actually PhD thesis was based on, where we explored network structures and looking at the sustainability of certain renewable resources. But then as we moved on, we discovered this new literature 4 to 5 years ago, where the field of socio-hydrology was being introduced. And we really took this process modeling to the Indus Basin. And I'm very pleased to see that some of our collaborators is in the audience today. So Professor Westport from MIT and Dr. Afreen Siddiqui, also from MIT. So together, the three of us, we wrote a series of papers. We looked at this process modeling, and really looked at the spatio-temporal evolution of various irrigation organizations across scales, from the national boundaries, provincial boundaries, to all the way down to canal commands. Many of our work is actually technology driven. We make gadgets, we deploy those gadgets, and we keep thinking in our minds that how would farmers react with these gadgets? How would irrigation managers react with these gadgets? And once again, this idea of socio-hydrology, of these human-water interactions and socio-ecological systems, very much at the heart of much work that is going on at the center. And then finally, what really caught our attention and what we were inspired by was that this field actually lets us explore things which are sort of come as surprises, so to speak. So the so-called irrigation efficiency paradox is something, as a year one's kind of a paradox, is something that we have recently looked at. And we have deployed techniques from socio-hydrology to really look at these kind of surprises and then connect them to practical scenarios of irrigation management within the Indus Basin. So that's a little bit of a connection from our side, why we are so inspired by your work, and we really hope to hear more from you and learn from you, and how to take some of these techniques and then apply them to the problems that we are looking at. So over to you, Talha. Please conduct the seminar.
Yes, thank you, Dr. Abu Bakr. And with this, Dr. Siva, please, over to you. Yeah, we look forward to learning from your talk.
Okay, thank you very much. Good evening, all. Assalamu alaikum. I'm really delighted to be here. I hope you can all hear me. Is that okay? Great.
Yes.
Great. First of all, I want to thank Dr. Mansoor and Dr. Abu Bakr for giving me an opportunity to present this talk to the folks at the BID Center today. As Dr. Mansoor already said, I claim that I'm only a hydrologist and not really a specialist in water resources management. So you have to bear with me on some of the things that I might claim in my talk today. And also, I have not really looked deeply at water management issues in Pakistan. Although, when I was studying at AIT in Bangkok, Thailand 40 years ago, I had many fellow Pakistan students who were doing PhDs in water management. And I came to know from them that irrigation water management in the Indus River Basin was an excellent example of scientific water management anywhere in the world, at least at that time. In my talk today, I'm going to take you on a tour around the world and present examples of the water crisis and share lessons that I have learned by looking at water management through the prism of socio-hydrology. Although I will not talk about it, socio-hydrology may have some bearing on why the Harappan civilization centered on the Indus River may have dispersed some 3,000 years ago. Okay, 3 years ago, I attended a conference in my hometown of Jaffna in Sri Lanka, and talked at public forums about the water crisis there. These are some newspaper articles that appeared following my visit. My talk today reflects some of the messages in these newspaper articles. More about Sri Lanka later. So I start with the definition of water security as the reliable availability of an acceptable quantity and quality of water for health, livelihoods, and production, coupled with an acceptable level of water-related risks. One of the first lessons that I have learned in the last 10 years is that water security is not just about water. In fact, many times it's not even about water. I will anchor my talk today on water supply management, aiming to meet the water supply needs of a community. Typically, from an engineering perspective, this boils down to matching demand with supply. except that it gets more complicated in that the infrastructure needed to meet the demand needs investment, which is itself a challenge in many communities. Even when this is possible, one often finds that there is a failure because insufficient attention is given to governance. The result is the water crisis. Even in developed societies such as the United States, if you may have heard about the city of Flint, Michigan, or even in affluent cities like Chicago, located right next to the Great Lakes, who cannot find a way to meet the needs of all of their citizens. Forget about large cities in Asia, Africa, or South America. It indicates that the water crisis is in fact, in reality, a governance crisis. It is more than about science, engineering, or economics. It is in fact social, which makes it a wicked problem and needs more than rocket science, as we call it, to solve. Governance forces us to make decisions involving choices or trade-offs. Our own livelihoods versus the environment, rich versus poor, upstream versus downstream, city versus rural, agricultural versus industrial, and so on. What is the balance between our short-term needs versus long-term consequences? These are all value judgments, which together form our culture. What kind of people do we aspire to be, for example? In traditional water management, the values that underpin our decisions are assumed to be fixed over the design life of systems that we build for water management. In the short term, this may be okay, but in the long term, culture and the values and preferences that underpin it are not fixed, and they themselves evolve due to our own lived experiences. So the failure to allow for the values and preferences and culture to change can give rise to, as Dr. Abu Bakr just mentioned, surprises, unintended consequences, which environmentalist William Odom once called the tyranny of small decisions. So I will, in the rest of my talk, I will illustrate this with a few examples taken from socio-hydrology. I always, in my talk, I always go back to this example because my introduction to socio-hydrology started from here. So I look at the so-called Murrumbidgee River Basin in Eastern Australia. Murrumbidgee is a sub-basin of the much larger Murray-Darling River Basin. Murrumbidgee underwent more than 100 years of irrigation development, I guess similar to Indus River, and which involved building a series of dams and reservoirs. You can see in this top picture here, series of dams and reservoirs, which allowed farmers to put more land to agriculture and thereby increase agricultural productivity and improve farmer livelihood. Essentially, it involved what I always call the positive spiraling. You know, you harvest land, you add water to it, you create wealth, and you invest some of that wealth in more dams, and then it allows you to harvest more land and so on. It's just a positive spiraling that unfortunately happened at the expense of the environment. So you can see here, irrigated area went up, rice production went up, population went up, everything was going up and up. This is the example of the positive spiral I was talking about. But it was all happening at the expense of the environment. Increased extraction of water meant that by the year 2000, not a drop of water was flowing to the ocean. And rivers and wetlands, the so-called billabongs in Australia, all dried up. This triggered a reaction in the community and fueled a green movement, which eventually forced the government to enact measures such as including laws to return water back to the environment, and with inefficient farmers giving up farming and migrating to the cities or moving to other industries. and with a consequent loss of population. So you can see everything that was going up, and eventually, as a result of the government actions, and of course there was a major drought, and then they started going the other way. We call it the pendulum swing. And we built a simple socio-hydrological model to describe this phenomenon, expressed in terms of a set of coupled differential equations that capture the hydrology, agriculture, population dynamics, ecology, and offer the social system that we expressed in terms of what we called at the time environmental awareness. The key thing to note here is that the model that I just presented here in the form of these 5 equations, only one part of it is hydrology. So in other words, it's an interdisciplinary kind of model. And I don't want to go into the details of this, but we were able to, using this model, we were able to mimic what happened over the 100 years. You can see on the left what actually happened, and on the right, the model output. So we were able to mimic what happened in the catchment. But more importantly, the lesson from the modeling is that the pendulum swing that we were seeing in the Murrumbidgee is a result of 2 competing forces, as you can see on the right-hand side, a yin and the yang, a productive force that drove the positive spiral, and what I call the restorative force that moved it back. And there's this balance between these two dynamics that results from these 2 forces acting against each other. With the human beings having to make the choice between their own economic livelihood and ecosystem health. So you can see on the left side of this panel, you can see that land and water are brought together by people for agriculture, which generates wealth, some of which is invested back in technology in the form of dams and irrigation canals to harvest more water, which allowed more land to be exploited, which makes the place more attractive and more people move in. So that's the positive spiral here on the left-hand side. On the other hand, exploitation of water leads to a reduction in flow downstream, which lead to environmental degradation, which lead to increased environmental awareness and activism, which then leads to a turnaround through government action to return water back to the environment. So this is the yin and the yang acting against each other. This is what we were modeling. Now this is a model. And I told you that the model was able to mimic what happened. And I'm giving you some more details about what actually happened through the model. So you can see on the left panel here, the water being extracted for agriculture, leading to reduced stream flow downstream, leading to environmental degradation, and that is leading to environmental awareness, which is forcing the turnaround here. So this is from the model what we are seeing. Now, obviously that was the model prediction, and interestingly, independent of us, what our idea was confirmed by an independent study by scientists at the University of Melbourne, who surveyed changing community attitudes about economic well-being and environmental health. And these things were quantified through independent analysis of newspaper articles in the Sydney Morning Herald for more than 100 years. And which showed that as concerns about the environment increase in the community, as in this green line, economic well-being decrease, and vice versa. These two are coupled to each other. And so our model was reflecting on something that actually happened in the Murrumbidgee River Basin. Now I want to move on to give you a few more examples of historical changes. So something similar to Murrumbidgee also happened in Western Australia, also a pendulum swing, but under slightly different circumstances. Here the story is forest clearing for agricultural crops. It's a very interesting story as more and more land was cleared of forest. Agricultural productivity rose, population increased, GDP increase and so on, so similar to what happened in Eastern Australia. However, over time, the replacement of forests by crops led to a change in the water balance, which led to rising water tables, groundwater table was rising, which had a negative effect of rising salinities. Basically, the rising water table brought up the salt that was already in the soil, brought up the soil, the salt to the surface, and that led to environmental degradation, loss of agricultural productivity, and therefore a turnaround in the and a pendulum swing, including in the GDP and population and so on. So very similar things were happening in Western Australia. So to address these issues that we're seeing in different parts of the world, including China, we were doing some work in China at the same time. So we refined, we extended our earlier model, the conceptual model to address the yin and the yang in the form of two loops, an economic loop and an environmental sensitivity loop, where we replace the environmental awareness variable with a more broad variable we call community sensitivity, which reflects community sentiments about economic well-being and environmental health, and which is rooted in culture. So we apply this model to other situations and contexts, which I will illustrate with a few more examples, including in China. So this is now I come back to the US. I take you to the Kissimmee River basin in Florida, which includes the city of Orlando, where Disney World is located. Over the last several decades, the Kissimmee River has undergone something like a pendulum swing. The basin used to suffer frequent flooding due to tropical cyclones that hit the area. The people of South Florida, you can see here, people of South Florida, southern part of the basin, convinced Congress and the federal government in the 1940s, at the expense of billions of dollars, to straighten the otherwise meandering river. So you can see the meandering river, they straightened it. This is the leftover from the straightened part of the river. So they straightened it as a way to reduce flooding, to increase drainage. However, in the intervening decades, with the growth of the Orlando area, new and more affluent people moved into the upstream areas, and they had different value systems, and they wanted the natural environment to return. So there was a competition between the value systems of two different groups of people, upstream and downstream. One group of people wanted a more pristine environment, the more affluent people in the upstream part of the basin, and another group of people wanted protection from floods. So in the end, unfortunately, the upstream people won out because they had more political power and they had more financial, they had more wealth. And the river was re-meandered back to its current state at the cost of more billions of dollars. And we were able to model this problem, this turnaround, using the community sensitivity state variable, as I explained to you before, except that we actually applied the community sensitive state variable to upstream people separately and the downstream people. You can see the community sensitive state variable here in this picture here. So they were two different value systems. The sensitivity to the environment and flooding was different, and except that together, when we put them together, the upstream people won out. So there was a power dynamics that was happening, and we were able to model that. Now, let me take you to China, the Xinjiang province in far western China. A similar problem of people making choices between economic well-being and ecosystem health in this otherwise hyper-arid and highly sensitive environment. Extraction of water for agriculture led to a drying of rivers and also terminal lakes, and the loss of precious, what they call Chinese poplar trees. The government, central government, imposed water-saving technology on the farmers in the form of plastic mulching. You have to see it to believe it, the extent of plastic mulching that was happening across the entire Xinjiang agricultural regions of Xinjiang as a way of improving the efficiency of irrigated agriculture. Now, this was dramatically successful, except that the improvement of irrigation efficiency did not lead to improvement of ecosystem health. As you can see in this picture, because farmers used the water that they saved through the plastic mulching back into increased productivity by expanding the irrigated area that they put under crops. So this is seen in the slide here. So you can see exponential growth in irrigation efficiency as a result of plastic mulching, and exponential growth in water consumption as well. So in other words, the intended water saving did not actually happen. So this is, we call irrigation efficiency paradox, and there was a PhD study that modeled this thing. Let me just go to another example of unintended consequences. Again, without going into a lot of detail, several of my colleagues have brought out a paper in Nature Sustainability by looking at examples around the world, the building of reservoirs to tide, especially in cities, to tide over the effects of droughts or increased demand. Now, this works very well in the short term. However, in the long term, it tends to increase demand. The moment you build a reservoir, in the hope that it will alleviate the demand, alleviate the shortage, you basically, the fact that there's the reservoir in place means that more people move in and the demand goes up, and eventually there's increased dependency and increased vulnerability as a result of it. So they overcome the water shortages in the short term, but they exacerbate water shortages in the long term. So this is documented through several examples from around the world. Let me go to another example of trade-offs. Now, I want to mention the flooding and evacuation of the entire city of Brisbane, Australia. So in 2011, the region, in this whole region of northern Queensland, was experiencing a major drought, the millennium drought. And operators of the flood control reservoir, flood control dam upstream of the city of Brisbane were concerned about keeping water in the dam high enough to cater to the water supply needs of farmers. Like you see in this picture here, you try to keep the water as much as possible in the dam, and they were conditioned on that because they have been experiencing drought for several years. Except that suddenly there was a tropical cyclone that came over and dumped record amounts of rainfall in the catchment area of the dam in a short period of time. And to avoid the dam overflowing and overtopping, they had to release water quickly and with little notice, and which caused the city to flood. So this involved a trade-off between flood risk and drought risk, and which the managers or the operators of the dam did not plan for, were not trained for. So all of these are examples of coevolution of hydrology and society, something the Greek philosopher Heraclitus had described as, no man ever steps in the same river twice, because it is not the same river and he's not the same man. Round about the time Heraclitus was saying this about 3,000 years ago, this kind of change was happening right here in the Indus River Basin. And the Harappan civilization began to disperse and collapse as a result. I hope I'm right, but that's what I'm thinking. So all of these, so the science of socio-hydrology was launched to deal with this coevolution resulting from the two-way feedbacks between humans and water. One of the goals of socio-hydrology has been to develop understanding of several phenomena or unintended consequences that arose in the usual practice of water management. In complex systems language, these unintended consequences are emergent phenomena that arise from the interactions of what I call fast and slow processes. So an example of the slow process is the variable I mentioned earlier, the community sensitivity. It's like the cancer that is growing in you. You are a healthy person, you are very active and physically, except that there's a cancer that has started to grow, and it takes its own time, and eventually it manifests itself. It's like that. It's a slow variable, and interaction between slow and fast and results in emergent dynamics, emergent phenomena. And the examples that I presented to you now so far are examples of emergent phenomena that arise as a result of multi-scale and cross-scale interactions between fast and slow, between humans and nature. So one of the lessons of socio-hydrology is that culture and social norms and values that come with it must be made endogenous to water management decisions. They should be part of the system. They should not not imposed externally and not assumed fixed. This is more important, as this paper shows. This kind of allowing for the culture to be endogenized is more important than making assumptions about rationality and utility maximization that underpin much of water management decisions that we make. Another challenge towards building more resilience into water management is to fully account for human agency, which is very hard. As this cartoon shows, the humans adapt to new information, including predictions of their own behavior. And this makes predictions very highly uncertain. So given the uncertainty of human behavior, the goal of predictions, we always use models in water management. The goal of prediction is not just to design the most optimal solution, but rather generate what we call the possibility space of possible future trajectories of human development under alternative choices and trade-offs that humans can make with values and preferences that are allowed to co-evolve together. So that is the introduction to socio-hydrology, in a very broad brush manner through several examples. There's a certain message that I want to communicate today. So I now go back to Sri Lanka and the water crisis in my hometown in the Jaffna Peninsula, in the northern tip of Sri Lanka. So Jaffna Peninsula has been experiencing a severe water crisis in the last 10 years. Now, Jaffna Peninsula here, as you can see the map of Sri Lanka here and the peninsula here, the city of Jaffna. And the peninsula is named after the city of Jaffna. And in fact, it is the cultural capital of Sri Lankan Tamils. And just as a point of interest, my own hometown is this red star here. I'm from here and I studied here in the city called Point Pedro. So compared to the rest of the country, Northern Province, and especially Jaffna, have had major water security issues for a long time, for hundreds of years. In fact, I would say the people of Jaffna are defined by the water security challenges that they faced for hundreds of years. Problems, unfortunately, exacerbated since the civil war that ended in 2009. So let me just give you some background, some hydrological background. So compared to the rest of the country, Northern Province, this is Northern Province and Jaffna Peninsula here. Northern Province have had highly variable water resources. The peninsula here itself has no rivers or freshwater lakes. This is so flat, it's extremely flat, and there are no rivers and no lakes, and water resources are highly variable. And it rains for a few months of the year, affected by the monsoon, and the main source of water is groundwater. And even the groundwater is very special. It's karstic. The aquifer itself is karstic, limestone aquifers, as you can see here. Highly variable, and in fact, the finding water is like a hit and miss proposition. You drill a hole in one place, you get nothing, and then a few 100 meters away, you get fresh water, that kind of thing. And the water is in these limestone cavities and concentrated only in a few pockets. You can see the main aquifers here in this picture, this one here, and this one here. These are the main aquifers. And the ground thickness of the groundwater lens is no more than 20 to 30 meters. And you have to also worry about the compounding effects of the ocean surrounding the peninsula, and also lagoons. There are lagoons that take salt water into the land mass. So you're basically the aquifers are surrounded by salt water, not at a short distance. So let me reiterate the water supply situation in the peninsula itself. So as I said already, no rivers or freshwater lakes, a heavy dependence on karstic groundwater aquifer, and the compounding effects of oceans and the lagoons. So if you overpump the groundwater, you're going to get the salt water come in. And so there's a freshwater lens floating on saline water underneath. So that is the water supply situation. Is highly variable in space, even for a small place like that. And the consequence of that is that there's no possibility of centralized water supply. There is no possibility of dams and reservoirs. So the water supply has to be highly decentralized. And basically the people of Jaffna Peninsula, they survived on a combination of rain-fed agriculture, rain-fed for rice cultivation, and irrigated agriculture for cash crops. So using groundwater. So that is the way that they survived for hundreds of years. And this also reflected on the historical human settlements. People depending on rice production, people depending on cash crops like chilies and tobacco and so on. And they relied on different sources of water. So here's an example of rice paddy. My own family were rice farmers. We had rice paddies like this that we owned, and we still continue to cultivate. And then we have other kinds of farmers who rely on groundwater, basically taking water from a well. And most of them at those times, when I was living there, were dug wells like this, going down to about 20 to 30 meters, depending on diesel power for irrigation, for pumping water. So that was the way that people lived for hundreds of years. And now let me take to what we call the mainland. So still northern province, but below the peninsula. And it so happens that in the mainland, we had a few rivers, which were mostly ephemeral and very little groundwater. So if you want to have agriculture, and during the time I was living there, not many people lived there, but later a lot of people migrated. So in order to persuade people to move into this area, the government had to build dams. So here's an example of a dam that was built to store water and use that water for irrigation. So this is the largest of those. So on the mainland side of things, depends on very few ephemeral rivers, very little groundwater. So centralization is not only possible, but was essential to encourage people to migrate and to settle in this area. And both rice production and vegetables were done and were highly productive, but they depended on stored surface water. And this reservoir that I showed you before, it was a key source of water. And as I already said, distribution of new settlements in this area reflected the availability of reliable water supply as a result of building these dams. Okay, so what is new now? Okay, so something happened. What happened was the civil war which lasted 30 years. I won't talk about what happened during the time. There was very little agriculture, very little economic activity. But at the end of the war, there was an intensification of agriculture. The people had to return to their livelihood. They had to rebuild their lives, and with government help, they started doing this, and there were major changes. One is the intensification included excessive pumping of groundwater. Electricity was provided, and instead of the dug wells, people started building deep tube wells, and then they pumped them using electricity. Free electricity was provided. So excessive pumping of groundwater and excessive application of fertilizer and pesticides to increase productivity. And also, as a result, with the end of the war, there was increased tourism, new hotels were built, and the hotel needed water for swimming pools and so on. So there was excessive pumping of groundwater, and also for all of the peninsula, all of the province, there was no sewage disposal. So that means that every house had a septic tank, and basically the human waste was going back into the groundwater. So the net result is the intensification of agriculture and increased increased industrial activity was nitrate and fertilizer residue was going into the groundwater, E. coli contamination due to lack of sewage treatment, and excessive pumping also meant saltwater intrusion. And all of them were contributing to impacts on human health. People were suffering from kidney diseases. All of this happened in the last 10 years. And also unreliability of groundwater quantity, drying up of wells, especially near cities because of excessive pumping. So things got really bad in a short period of time as a result of these increased intensification of agriculture and industrial activity. So maybe I'm coming to the end of my talk, but just give you, I mean, when I was there 3 years ago, I gave a lecture and basically I studied the situation, and based on my experiences of socio-hydrology from around the world, I was giving advice and basically I lectured and advocated long-term, broader and more holistic and inclusive kind of solutions. For example, make agriculture more water efficient, change to drip irrigation, change to less water consuming crops, start charging for groundwater and so on, and structuring of the economy, move agriculture to the mainland through incentives, bring non-agricultural, for example, knowledge-based industry to Jaffna, and so on and so forth. In other words, I was advocating going back to the old ways, meaning decentralized water management. That was my preferred solution. Unfortunately, the solution that is preferred by the engineers there and the politicians and funding agencies, for example, the Asian Development Bank, their solutions were, two kinds of solutions were being discussed at the time 3 years ago. One is to raise the water level at the Irrigation tank and then divert water from the tank there, from the mainland into the peninsula. And the problem with that is it is very expensive on the one hand, but then you're taking water away from the mainland, and so you're jeopardizing agricultural productivity in the otherwise untapped potential in the mainland. That's one problem. And the people of the mainland were also protesting at the time. They didn't want the water to be moved. So there's going to be a conflict, transboundary conflict between the mainlanders and the peninsula people. They are the same people, except this is creating a new problem. And the other solution favored by the Asian Development Bank was desalination of seawater, and they had no, the people who were propagating this, they had no concerns of who will pay for the maintenance, who will pay for the electricity, who will give you electricity, and also no consideration for the unintended consequences of that, of delivering water to big cities like Jaffna and so on, without a sewage treatment plant yet. And also, nobody is talking about the groundwater contamination issues, which is the problem in the first place, that caused the problem in the first place. So instead of solving the problem that is there, they're creating a new problem and solving that problem, because that is what is favored by engineers and politicians. And in fact, just in the last few months, the desalination of seawater won. So basically, the government has approved it. That's going ahead, and I shudder to think, I really worry that in 50 years' time, we are going to have a whole bunch of new problems in Jaffna Peninsula that we did not even anticipate. Because people have no say in this matter. So in other words, we are not learning the lessons of the rest of the world in this area. So that is a depressing story that I want to finish the talk with. So my final lesson here is that the water management decisions must involve a broadening of the conversation, to bring diverse perspectives, to be more consultative, to be more inclusive. But in most parts of the world, we are not learning the lessons from the failures of water management. There is still a heavy focus on what we call the hard path infrastructure-based solutions for water management problems. If you look at the UN Sustainable Development Goals, water lies at the core of several of these, including poverty alleviation, environmental health, and so not just fresh water. So when you don't account for these interactions more inclusively, you have the kind of unintended consequences that are listed here in this slide, okay, that we have studied in socio-hydrology, and there is no real water security. So what I said at the beginning, water security is not just about water. In my belief, in my experience, it holds true still. So let me leave you here with a quote. This goes back to the 2012 presidential election in the US, and when Obama won, and this political blog was written by somebody to discuss the election in Ohio. The Ohio was forecast to be going Republican, and because of Obama's ground game, Obama won narrowly. And so this guy wrote, and I just read the blue quote here: organizations with narrow fields of vision becomes institutionally incapable of spotting where the icebergs ahead are located. So that is my main message. I think we need to learn the lesson. We need to be more broad and holistic looking. If I have time, I just want to finish one more slide. Now, this is in your locality. I was in India 2 years ago in 2019. I got to know about this problem. You probably already know about this. I used to think that Beijing, China was the smog air pollution capital of the world. No longer. It is New Delhi now. And the smog that's happening in New Delhi is not because of fossil fuel burning or vehicular traffic in the streets and so on and so forth. It has everything to do with water management. So the state of Punjab introduced a law in I don't remember 2009 or something. Introduced a law to delay the harvesting of rice. So in other words, the farmers were asked to delay everything for the by 1 month, because that way they can save on water, because the rice production in Punjab province is groundwater through irrigation, through groundwater pumping, and by delaying this by 1 month, they were hoping that they can this harvest period can coincide with the monsoons, and that way they don't have to irrigate so much. That was a good intention, except that the delaying of the harvesting in the Punjab, as opposed to Tamil Nadu in the south, the farmers have a habit of burning the stubble that's left behind after the harvesting. In Tamil Nadu, they actually use it for cattle feed. But in the Punjab, they burn. And the burning 1 month later coincide with the change of the wind patterns. So basically, at the time they burn, as you can see here, lots of burning all over in Punjab and Haryana. The wind direction changes, and the winds take the smoke in the direction of New Delhi, and that causes the smog in New Delhi. So, in other words, an unintended consequence of water management decisions made by Punjab. So let me just finish my talk there, and I'll be happy to answer any questions. Thank you.
Thank you, Dr. Seva, for the very enlightening talk. And I think there are a lot of lessons for us to learn, because a lot of the stuff that you were talking about are directly related to the situation that we are facing here, especially in the Indus. So we are on the cusp of a lot of programs. A lot of technology is ready to be proliferated. Programs are being started. People are introducing it in the government, also locally being adopted. We have private companies that are emerging. So all of this needs to be, someone needs to think about all of this. And I want to open the floor for questions and answers. So for all of you who are attending You can see a Q&A option on your screen, and you can just write your comments or your questions over there, and we can read them out, and Dr. Siva can respond to them. So we already have a question, so let me read it out. How is socio-hydrology serving in understanding the water issues differently, while socio-ecology and IWRM have been there for years?
Okay. Again, as I said, I'm not an expert on IWRM, but I think that the main, if I understand it correctly, the main difference is that the main difference is in the endogenization. In other words, in IWRM and traditional water management, you look at you impose scenarios. What you want to achieve, what under what circumstances, and then you put them into the models and make predictions, and then on the basis of prediction you do optimization, you benefit cost calculation, and choose decisions that will advance what you want to achieve. But in socio-hydrology, we always used to claim that the socio-hydrology is more like the science underpinning IWRM. So in other words, what we do is we look at the outcomes of water management. So water is being managed. Water managers are managing water, and we are just observers as scientists, look at what's going on and learn from what's happening, and then use the lessons that are learned back into more advanced water management decisions. So in other words, there's a difference between IWRM and socio-hydrology in the sense that that we allow for these two-way feedbacks to take place, and it's like you're pilot of an airplane that leaves Chicago in the direction of Tokyo, and along the way you have weather changes, you adapt to the weather changes, you change the flight path, and so that's a big difference. So you start with a certain decision, and then you allow for the decision to be adapted along the way. So that's the big difference between the way that socio-hydrology looks at it and the way that IWRM looks at it.
Okay, thank you. And moving on to the next question by Dr. Afreen Siddiqui.
Yeah.
So the question is, what are your thoughts on endogenizing political economy in socio-hydrological models? As you have shown, the emphasis on endogenizing culture and change in values is essential in modeling development and use of water systems. As values are put into action and manifest in decisions through political agents and processes, perhaps there is a need to specifically endogenize the political economy on the socio-hydrological models. What are your thoughts?
I'm not an economist. I'm definitely not a political economist. But this is something that, in fact, we are debating actually in the socio-hydrological community. How far can we go, in this direction? Because can some of these things be even modeled? I mean, I have no expertise in economy or politics, but especially when it comes to political economy, political ecology. How quantitative are they? So I think clearly, we may be able to push the boundaries a little bit more in endogenizing some of these things, but I don't know how far we can go. So I have really difficulty, in the sense that I don't have a lot of expertise in this. I don't want to even hazard a guess about it, because people will attack me. Because yesterday I had a conversation with some social scientists, and they were really concerned that in their community they cringe at some of the things that we are doing in social hydrology. in the name of social process modeling, you know. So you have to, I mean, if you're going to move in that direction, I think we need to do this more collaboratively and with political economists. So it requires a lot more collaboration than what we are doing now. So our community of socio-hydrologists must be broadened to even have confidence in this, you know, because we are already being under attack, you know, that you don't know, you know, people have told me that you don't know anything about social science. Why are you doing this? You know, so there's always a danger. But I think I would welcome, of course, if some political economists decide that this is worth doing, then I think that we will be more than happy to you know, engage with them and move in that direction. Absolutely, it has to be done. But you know, how far we can go is a problem for me.
Okay, thank you for the answer. And moving on to the next question.
Yeah.
So the next question is by Dr. James Westcott. So I'm reading it out. In the Jaffna example, you provided a good yin-yang representation of the problems. Might a socio-hydrologic approach explore the possibility space and range of choice more fully? For example, desalination of brackish wells, excessive water reuse, etc.
Absolutely, Jim. Yeah, in fact, I have actually started to move in this direction myself. In fact, so in other words, through the help of some students, what I want to do is, because the people of Jaffna, you know, I mean, as an example, you know, they are being, you know, informed and advised by traditional engineers and politicians, and so they don't have a clue as to what is happening, as to what should happen in the future. So I think the idea, I think what Jim implies is what I had also in mind, is to create a social hydrological model of the system, Jaffna Peninsula and the mainland together. Build a model. It could be a stylistic model, a simple model, and use the model to create a possibility space. You know, these are the options that you have, and if you take these options, this is where you'll end up in. So you create that space, and then whatever comes out, you go and present it to the community and get engagement. So they get sucked into this, so they can look at what's in store for them in the future, and they might begin to be better informed, and then they can go to the politician. This is not what we want. This is what we want, and so on. So a model like that would be extremely valuable as an educational tool, even to provide information and you know, create awareness and also generate you know, even actions, people, you know, to get the people involved. So I absolutely think that this is the way to go. I'm trying to do this through some of my students. Hopefully, we will make some progress. But you know, education is extremely important here, because the people are, you know, in fact, when I gave my lecture in Jaffna, many people complained to me, saying that the government is giving us water. Why are you going against it? That was their thinking. The government is giving us water at the cost of millions of dollars. Why are you why are you speaking up against it? So you know, the only way I can answer that question is to actually, you know, do some work in this area and show them that if you make these choices, this is where you will end up in 50 years' time. You will not be alive to see it, but your grandchildren will see it, and that information has to be provided. Thank you.
Thank you, Dr. Seva. And with that, we have approached the end of our time slot for the webinar. I thank all of the attendees for participating, and just to let you know, Dr. Sivapalan has kindly agreed for us to upload this recording on our website, where the schedule is available. If you missed any part of it, you will also be able to view the presentation and the video over there. So with this, at the end, I would like to thank Dr. Sivapalan again for taking out time and enlightening us with this, with these very relevant ideas. And we hope that so you mentioned that the Indus is an area where you have not worked yet, but we would like to see this as a possibility to engage you in a lot of similar problems that we are facing in the Indus as well. So with that, I conclude the webinar, and everyone take care, and I hope to see you in the future sessions as well. Goodbye and assalamu alaikum.
Thank you very much for giving me this opportunity. Thank you.